Okay guys, it looks like we're back to video learning, so bear with me. I'm going to do a very short um, video on single slit interference. This is instead of obviously double slit that we did prior to the break. Um, I'm not even going to go through the theory. I'm basically just going to give you the equation and say, hey, memorize the equation. I hate doing that, but I don't think it's worth the derivation time. It seems like single slit shows up very infrequently on the AP. I just don't want you to be the lucky year. So it's going to be a very similar discussion of what we did with double slit wave interference. And it takes advantage of something called Huygens principle, which is kind of strange but seems to work well. So the idea is you will get interference through a single slit. And you might ask, how does that happen? Because obviously the double slit, you have two waves coming through and they interfere. But with the single slit, it uses something called Huygens principle, which says here we have a plane wave or a series, a train of plane waves coming into a gap. And when these waves arrive at the gap, each point along the wave acts like its own point source. So you can treat this blue dot on the top like making a ripple, like in a pond. If you dropped a rock into a pond, it would make a bunch of ripples. And this point will make ripples, and this point will make ripples. And so all these points, there's an infinite number of points in here that make ripples. And obviously, if that's the case, then you'll get interference of the crest from one ripple, and the crest from another ripple. You'll get interference. So that's the basic idea behind why you get single slit interference is Huygens principle. Now, one thing to note is that it's the exact same situation. So if we have a single slit, we have monochromatic light, just for the sake of being easier. You can get interference patterns on the screen located some distance away. You can actually see this if you're so inclined to. You can actually take your two fingers of one of your hands and put your fingers close together side by side and leave a tiny, tiny gap between your fingers and look at the light in your room. And you may see a bunch of parallel bands. Unfortunately, I don't have a picture of this, but you can do the same thing if you take two pencils. Normally in class, we take smart pencils, which have no value as far as writing, and we take two smart pencils, we put them parallel to each other, very close together, and then we look up at the ceiling at one of the lights in the classroom, and you'll see these black and white bands, dark and light bands, and that's caused by single slit interference. So you can see that, and you may have noticed that before if you've done that with your hands before. As far as the math, as far as the equation, there's a PhET simulation for this. It's very difficult to actually get it to work well, so I'm not going to bother. But the basic equation is exactly the same as the equation for double slit, except it's in reverse. So the equation I'm going to give you is for destructive interference. It's for the minima show up on the screen. And one thing to note, and different books use different notation, so I'm going to show you the notation that seems to be more common. You may recall that when we did double slit, the distance between the gaps was called D. Well, here they call it A. It's the size of the gap. They've also used the approximation that we talked about in class. You don't really need to do that, but if you want to, go ahead. The other thing they use is they use M instead of N. I use N as the integers 1, 2, 3, 4. They use M for some reason. So it's the exact same equation that we did before for double slit, except this is for the areas where there's destructive interference. And again, I'm not going to drive that out. If you want to know, Google it. So again, this is the summary page. If you want to find the single slit interference patterns for destructive interference, it will be A sine theta equals N lambda or D sine theta equals M lambda, whatever you want. And again, everything's exactly the same. So that's the single slit interference pattern. Like I said, I've only seen this ever show up on the AP 1 year. They had one question about it, so it's not. And obviously, if you have symmetry, if you're going to have destructive at these intervals, then the constructive will happen exactly halfway between. So if there's a destructive here and a destructive here, well, constructive must be exactly halfway between. So everything's equally spaced, and you can find the location. This is actually kind of nerdy, interesting. This is not my house, but it's a very similar picture. One night, my wife was in the bathroom getting ready for bed, and she had the door cracked open. And on the floor, I saw this pattern of bands on the floor. And of course, my mind started thinking, and sure enough, this is single slit diffraction, the light coming through the small opening of the door. You actually get this interference patterns up. It's extremely nerdy. I tried to explain it to my wife. She was not interested, went to bed. But anyway, this does happen in real life, but again, not a big deal. We're going to do thin films next, so that's much more involved. So I'm going to stop here on this video. And again, you can hold on to that. We'll see what happens as far as school closing.